Okay, so good afternoon for this audience and good early morning for that audience. It's about 8 o'clock in US. 9, 8.
9, I think, yeah.
Yeah, so we have VP Nair today from City College, and this subject is again about fluid dynamics. Sorry. And diffeomorphisms and anomalies. We have 1 hour, right?
Okay, thank you. Thank you, Paul. Thank you, Andrea, and all the other organizers. These are difficult times to organize a workshop, but you have done an excellent. Thanks for the invitation. As advertised, I'm going to talk about topological terms and diffeomorphism anomalies in fluid dynamics. It's something we have mentioned before. So let me start by pointing out the obvious, which is that there has been a lot of interest recently in gauge and gravitational anomalies in many aspects of physics, but also in fluid dynamics. And in the context of fluid dynamics, it is partially motivated by some physical contexts which are interesting. In high energy physics, there is a so-called chiral magnetic effect, which is expected to be relevant when you consider slightly off-center collisions of heavy nuclei, as they do in Brookhaven or LHC. And the core-gluon plasma state is in a fluid state, and you can have effects of chiral anomalies there, one of which would be displayed as the chiral magnetic effect. It's also relevant for quantum Hall fluids or superfluids, and some of that we heard today morning from Paul. What I'm going to do here is to focus on a related issue, but it's a little more subtle and nuanced than just straightforward anomalies. For the description, I'm going to use a group theory-based formulation of fluid dynamics. The key observations behind that, what leads to this group theory-based formulation of hydrodynamics is listed here. For example, let me see if I can do this. Yeah. Point particles. You know, in the modern way of looking at things, point particles are described as unitary, irreducible representations of the Poincare group, plus, of course, additional symmetry groups, which may be relevant if there are internal symmetries or gauge symmetries. And we also know that the unitary representations can be obtained by quantizing actions which are defined on orbits in the group. Okay, so the so-called coadjoint orbit actions. So the idea is to describe them, number of them, and do a Lagrange trick of coarse graining to obtain a fluid description. Okay, that is the formalism that I'll be using. And using that, we can actually write down an action for fluid dynamics. It's possible, in fact, to write down a general fluid action for the standard model, including all the anomalies that one normally encounters in the standard model. And if you simplify it in appropriate context, you can get things like the chiral magnetic effects, the chiral. Okay. Now, the subtle point I mentioned is best exemplified by talking about sigma models. So I'm going to say something about sigma models, where, recall, sigma model is basically describing a map from a base space, which is spaced on, to some target manifold. Okay. Now, it is possible sometimes to have a conflict of diffeomorphism invariance between and the target space. And this conflict can manifest as anomalies. And that, I will give you an example of that, and that will set the basic paradigm for what I'm going to talk about today. Okay, so once we have that, you know, I want to argue it can occur for fluids as well, not just for sigma models, because fluids can be, in the group theory way of looking at it, fluids can be posed in a way very similar to sigma models. Now, the immediate motivation for what I'm talking about, anomalous algebra, which was found by Paul Wigman and Abanov. They considered a fluid of vortices. So vortices themselves are treated as point particles, and you consider a secondary fluid made of these vortices. And then you look at their dynamics, including, in particular, commutation rules for the energy bound tensor. Okay. Now, the Hamiltonian dynamics of fluids was obtained by Kirchhoff in the late 1800s. Already in the 1895 edition of Lamb's book on hydrodynamics, which is one of the old classics, you actually see several sections devoted to Kirchhoff's work. It's actually very beautiful, very nice mathematical formalism. Now, the key result that emerges from Kirchhoff's analysis is that, if you consider a vortex line, there are two transverse positional coordinates. There's one along the vortex line and two transverse. The two transverse coordinates are Poisson conjugate to each other. Okay, that is the essence of Kirchhoff's work. Okay, once you understand that, then of course you write a Hamiltonian and you can write down the equations for the vortex flow. Okay, so what Paul and Sasha Abanov did, they considered a secondary fluid made of a number of vortices in the underlying fluid. Do you think if I use this, the Zoom can see that also? No, okay. So I had to point with this, yeah. So using Kirchhoff's work, they were able to quantize the vortices and then obtain the quantum hydrodynamics of this vortex fluid. And that's where the anomalous commutator algebra came up, okay? So you look at the algebra of the generators of diffeomorphisms, which are the spatial components of the energy abundant tensor, the 0I components of the energy abundant tensor. You look at their commutators and you find that there is an anomalous result. Now, why is that bothersome? Well, this struck me as something a bit unusual for the following reason. If you look at gravitational anomalies, if you look at where commutator anomalies come from, extensions of commutator algebra, we know that they are related to anomalies via descent equations, right? How do we formulate anomalies usually? We go 2 dimensions higher. We write down the index density in D+2, so to speak. Then you write down the Chern-Simons term associated with that, that's in D+1. Take a variation of that, that gives you the anomaly in D dimensions. Take one more variation of that, you get a 2-core cycle, which is the commutator anomaly, okay? So therefore, it's obtained via descent from the gravitational anomaly or gauge anomaly, whichever is the case. But we know there are no gravitational anomalies in 2+1 dimensions. There are no gravitational anomalies in 3+1 dimensions, and so on. So how could you possibly get a commutator anomaly? This was the puzzle, okay? So that is what motivated me to look into that. And I'm going to tell you that it's related to the subtle issue that I mentioned earlier. So let me say a couple of things about what kind of results we will get and how we're going to proceed. So what I'm going to do is to consider the standard Lagrangian for fluid dynamics. I'm going to add with some topological terms, just as you add Vesumino terms to usual sort of sigma models. One such topological term, I will argue, leads exactly to the anomalous fluid dynamics that Paul constructed, okay? There are, then of course, once you think of this in this framework, you can extend it to other dimensions. You can look at 3+1 dimensions, for example, and we'll find a certain central term which has been noticed in the context of fluid dynamics on a 3D torus more easily, okay? Finally, I will argue that there is another topological term that you can add in 3+1 dimensions, which can be related to a fluid of knots in a large number of vortices. Instead of considering straightforward vortex lines, what if the vortices knot it themselves, okay? Can the knot propagate as a particle, and can we make a fluid dynamics of that? So, okay, so that's what I'll be talking about. But now let's start getting into the details a little bit. Oh, I forgot to mention this. This is an interesting point to say. So how does this, relate to the work that I mentioned by Paul and Sasha Abanov? Well, a good analogy to keep in mind is what happens with the Weismann-Witten theory. Okay, so for that theory, or bosonization, if you like, non-abelian bosonization, how do we think about that? One way is to say, I start with fermions, I compute commutators, current algebra, I take care of Schwinger terms by careful point splitting analysis, I derive an algebra. Okay, and then I notice that if I now simply write down the Weismann-Witten theory and do the classical Poisson bracket construction of the Weismann-Witten theory, that gives me exactly the same algebra. Okay, and remember, Witten's analysis based on Katz's theorem that this algebra has a unique representation for level number 1, and hence these two are equivalent, hence bosonization, right? So it's a bit similar. The analogy, the analog of the point splitting analysis has already been done by Paul and so on, and they got this algebra. But we asked the question, is there another way to think about it directly in terms of an effective action? Okay, and that's what I hope to show you. Okay, there's also vortex particle duality. There is a lot of discussion, and this may have some relevance to that, but I won't say anything more about it. The key reference is this paper from last year. And now let's get into the details. Okay, so the sigma model I want to talk about has a target space, which is the complex projective space in 2 dimensions, which is SU3 mod U2. Okay, now this is a Kähler space. There is a Kähler form given by omega here, which is this one. I can write it as D of some potential A. And that potential can be written in terms of a group element U. This is not moving very fast, but okay. Like so, in this equation here. So I take an SU3 group element. I take the TA, the hypercharge, the last generator. Take a trace like this of U inverse du. That is a potential. It is not well defined on CP2, as you can see, because if I make a right translation of U by a TI direction, I notice that A shifts. So A is not defined, A is defined on SU3, but not on SU3 mod U2. Okay, but if I take DA, that is obviously well defined on SU3 mod U2. Okay, that also tells us that if I take omega wedge omega, that is something that is close but not exact, because the exactness requires me to go to the full SU3, not stay in CP2. So that is an element of what you might call H4, the 4th cohomology group. Okay. So the action we want to consider is this. Take the standard sigma model action, which is right here, this first term, with the metric of the target space, capital GAB, the fields, and then I add to it this term, where capital gamma is a potential associated to this cohomology element here. Okay, so write this as D of gamma, add it. Oh, this is moving. Okay, here we go. Okay, D of gamma, and add that gamma as the potential term, and you construct it. So this is our extra topological term in this context. And what we then do is simply go ahead and calculate various things. So let me show you how that works. First, let's take a look at this. We are talking about a differential form here. So it is insensitive to the metric of my base space. Hence, it does not contribute to the energy moment tensor, because the energy moment tensor is the variation of the action with respect to the metric. Okay. So the entire energy moment tensor comes from this first term. The only thing that the second term does is to change the canonical structure of the theory. Okay. So here is the energy moment tensor. It is only the usual looking terms. And then I can write down the generator of the diffeomorphism, x goes to x plus something, like so. It's given by the T0I component of this energy moment tensor. And I can write it out as shown in that second set of lines there, second equation, okay? So I take the 0I component and write it down. Phi dot is replaced in terms of the canonical momentum via this equation here. Oops, okay, here we go. Okay, so notice that the right-hand side, when I replace phi dot by delta delta phi, has an extra term gamma, which comes from the extra term I added. So that looks like a covariant derivative on the target space where gamma is the connection, okay? So that's why I wrote it in the second line of that equation as capital D sub A. And so now we simply take the commutator algebra, straightforward to do, no big surprise because something looks like a covariant derivative, you would expect that the commutator would also involve the curvature associated with that covariant derivative, okay? And indeed, it works out. Here is the commutation algebra. You notice that you get the usual terms. The terms shown in black are the usual terms that you expect for diffeomorphisms. The extra term in red comes from this extra gamma term, and that is, if you like, an extension of the algebra, okay? It is like an anomaly term in the commutator algebra. Okay, so that is there, fine. But then I notice, of course, that if you look at this expression for t, that is an ordinary derivative term delta delta phi and a connection term gamma. Well, if I drop the connection term gamma by hand, obviously it's going to just do the coordinate transformations on phi. So therefore, if I define a new energy abundant tensor script t, which I show here in this equation here, which is the old t minus this gamma term, then this will obey the usual anomalous, non-anomalous commutator algebra. Okay, so that's okay. The problem, of course, is that the subtraction term that I do is proportional to gamma. And gamma, as I told you before, is not well defined on CP2. I need to go to the full SU3 to make sense of that. So this is not proper redefinition. This is not quite an acceptable one. And therefore, I have this conflict. If I'm willing to give up invariance with respect to, if I only talk about well-defined quantities in terms of CP2, then I am stuck with the anomalous commutator algebra. If I give that up, I can get ordinary, there is no problem with the base phase diffeomorphisms. So there is a conflict, and that's exactly the kind of structure that we're going to find, okay? Okay, so that is the sigma model. Now I talk a little bit about vortex fluid. So I will phrase it in the language of superfluid helium, but as we heard earlier today, you can do it for quantum Hall systems as well. So if I take rotating superfluid, the rotational angular momentum gets transferred to vortices, and large number of vortices are generated, and the spin carried by all those vortices basically take up the angular momentum that you impart by rotating the fluid. Okay, so this creates a state that you might call a state of chiral flow. Oops, where this is the state of chiral flow. Notice that all the vortices are going in the same direction, and they essentially are related to the angular momentum I have imparted to the system. Okay. Now, when we talk about vortices, they're effectively two-dimensional. I'm going to do essentially 2 + 1 in this context. So we write the complex coordinates x plus iy. The equations of motion are given here. Omega is the overall angular velocity. And these equations of motion are essentially the ones that I mentioned earlier, come from Kirchhoff's work. Okay. And the Hamiltonian, also written by Kirchhoff, is displayed there. There is a term proportional to omega. There's a term proportional to the individual strength of the vortex that you find here, this gamma here. This gamma right here. Take them all to be the same, and then you can write down, that's what I have done here, Z and Z bar are canonically conjugate, as you see from the equation on the right side. Okay. So having this Hamiltonian, the canonical and the commutation rules, if you like, we can write down the ground state wave function for n vortices, and then based on that calculate commutators of the energy momentum tensor or the momentum density. Okay, so that's what was done, and it leads to this algebra that I have displayed here. This is from Paul's paper. The notation has been slightly changed because I wanted to agree with other things I do. Okay, but one should think about this algebra as obtained in the sense of being weakly true, acting on the ground state wave function, because it is dependent on the choice for the ground state function. Okay, now I also want to say that the density of the vortices must be related to the overall angular momentum. You sort of see that from this equation here. If I import a certain angular velocity and angular momentum, if everything is entirely transferred to vortices, then I can say that that is proportional to the number of vortices. Okay, but if the vortices themselves move around and create their own vorticity of motion, I had to subtract that out because keeping that would be overcounting. Therefore, one gets a constitutive relation rho, which is proportional to omega minus the little omega. Okay, this last equation shown here. Okay, so this rho on the left hand side is the number density of vortices. Rho bar is omega, and little omega is the vorticity of the vortices themselves. Okay, I call it a constitutive relation, but this is also the charge neutrality condition if you use the quantum Hall analogy. Okay. Okay. Now we want to construct an action which leads to this result. So what we are going to do is to use the fluid dynamics description in terms of the Clebsch variables, the velocity for a fluid. You can parameterize in terms of these three parameters here, theta, alpha, and beta, the Clebsch parameters. And once I have the Clebsch parameters, I can write down an action. Basically, the Clebsch parameters, theta, alpha, beta here, determine the canonical structure. They are the terms carrying the time derivatives, and the second term in square brackets is the Hamiltonian. Okay, so that's just a standard first order form of the action. You can introduce an auxiliary variable j, coupled like so. If you eliminate the auxiliary variable j, the space component, then you go back to the left side of this equation. Okay. Now, it's possible to write down, for our purpose, it's simpler and nicer. If you write down the Clebsch parameters in terms of the group variables, I introduce an SU11 group element shown in the last line here. U and U bar are, those are complex functions, so there are two of them, roughly speaking, 2 degrees of freedom. I have the sigma 3 theta by 2 on the right hand side, so there are 3 variables there appropriate to SU11. You can check that this is a good parameterization for the group SU11. Okay, alpha, and if you use that, you can write the Clebsch parameterization as I have shown here in this equation. Alpha and beta are related to U and U bar. Okay, now let me just make one observation here. Okay, first of all, I go back and notice that this term, by writing the auxiliary field J, I can think of rho as J naught with time derivative and Ji with space derivative. So I can combine that in a relativistic looking form, like so in this equation. And the rest is Hamiltonian, things specific to the fluid. I just call it f of n, where n is the square of J. Okay, so that action works for a relativistic fluid. The nature of the fluid or the specific characteristics of the fluid would be carried by the function f of n. Okay, the first term is simply giving you the canonical structure. Okay, and in fact, if you take this and vary with respect to the metric and write down the energy moment tensor, you can bring it to this form, which is a perfect fluid form. Okay, and J is related to U, or rather I define U, which is a 4 velocity in terms of J like so, okay, which is consistent with J square being n square. Okay. So, so that's just the standard fluid mechanics formulated in group theory language, okay? And we have an action for it. And that's what I'm going to use. Okay, yes, please. Yes, yes, indeed. I'm going to say that, okay? So if you are doing just classical Klebsch parametrization, as you read about in hydrodynamics books, it may seem a little strange what I'm doing here because theta is a compact direction. Where did the compactness of theta come from? Okay, so I want to first argue, I'll come to the SU2 in a second. So why is that? Okay, well, let's take a look at the commutation rules implied by this canonical structure here in the top line here for the action, this term here. And that is the following. The relevant one for my discussion is this particular one. Okay, rho carries out right translations of the group element G. That's what it does. Okay. So if I use that, then I realize that if I take G and conjugate with this particular element, namely I choose integral of rho to pi I, of course, and then look at that, G is flipping sign under this transformation. Okay. But all the observables I'm going to construct, because it goes through the Klebsch parametrization, will involve 2 powers of G, G or G minus 1, okay, either way 2 powers. As a result, it tells me that effectively this operator U can be set to 1 on all the observables. If I am setting it to 1, that means integral of rho is effectively an integer. What does that mean? That means by making theta compact, as I have done here, it tells you that the fluid is composed of an integer number of particles. Okay, there's nothing surprising about it. You might say it's actually a good feature, not a bad feature of the theory. Okay, so it is okay to have theta as a compact direction. By the same token, if I were to quantize vorticity, notice that from here, if I take this is supposed to be the velocities, as you see from this equation here. If I take the curl, theta disappears, vorticity is in this alpha d beta part. And if I insist on vorticity being quantized, effectively alpha beta directions must be made compact. Okay, that means instead of talking about SU11, I should really be using SU2. Okay, that's the issue. What I'm going to say later is insensitive to which one you use. You can use either one appropriately. Okay. Okay, now let's proceed. So I have the action in this top line here, and now you have the canonical structure there, as you can obviously see, and now you simply compute energy abundant tensor. It's given in this equation here. Take the TI0 component, calculate the commutator, standard, nothing anomalous, everything is fine, okay? And the vorticity, I might say, dV is related to this object here, which will show up also in what we do later, okay? So everything looks fine, standard ordinary fluid dynamics, nothing anomalous. Now we ask, what kind of topological terms can I add to this? If I were to take this action and add topological terms, what would I do? There are several terms that you can think of. I'm going to focus on 2. In the paper, of course, I discuss other cases as well. But for our discussion today, these are the ones important. What I call I2, G inverse dG cube, trace, that is well defined for this group, wedged with some C. We are in 4 dimensions, then C should be a 1 form. We are in 2 plus 1, C should be a 0. Okay, that is so that is a term, topological term I can add. Another possibility is to take sigma 3 G inverse dG itself, wedge with omega. Omega should be a 3 form or a 2 form appropriately. Notice that this is not the canonical structure because that had a rho or J in front of it. Remember here I had J naught, which was rho. So this is different. This is a purely topological term. Okay. So what I'm going to do is to analyze the I3 term, the second of these terms first, So I consider an action, which is just this term, which is coming from the standard action I showed you, the first term. This is the topological term. Then, of course, there is Hamiltonian. I am focusing on the canonical structure of the theory, the commutator algebra. So I'm not going to worry about the nature of the Hamiltonian too much. And what I'm going to do is to take this omega, take the dual of that, and call it rho bar, which is appropriately epsilon ijk omega ijk, or the one with two indices on three and 2 dimensions appropriately. Okay, so put that here. So I have rho minus rho bar times this. So the canonical one form, which is obtained by looking at what survives. Remember, the canonical one form comes, I take the action, vary it. There is a surface term. Take the surface term on the top time slice and the bottom time slice. Take the one on the top slice. That's your canonical one form. Okay, so it's easy to read off from here. And so here it is. Okay. Secondly, I can also take the energy moment tensor. From what I said earlier, the topological term will not contribute to the energy moment tensor. Therefore, I can write down straightforwardly what the energy moment tensor is. I do that. I will not bore you with all the details of the calculation. It's a little bit tricky, but it's not terribly complicated. And here is what you find. The commutator of the energy moment tensor, just the space components. So these are the ones which generate the diffeomorphisms. They look like this. The first term on the right-hand side, exactly what you expect for the generators of diffeomorphisms. Second term is the anomaly. Okay, so there is an anomalous term. Psi and psi prime are just the test function, so we don't need to worry too much about that. What multiplies it is the vorticity, the curl of B, and then there is this factor involving rho and rho bar. Okay, so there is an anomaly that you find. Okay, is it a true anomaly? It's not a true anomaly in the sense of being a non-trivial co-cycle if I can redefine my energy moment tensor and get rid of it. Okay, it is what you might call homologically trivial if I can redefine my energy moment tensor to get rid of it. Okay, can we do that? And the answer is yes, of course, because if I subtract this particular term, it's not very difficult to see. Remember, there is a rho bar, which is the new added term. If I subtract a term proportional to that, rho bar times the velocity, psi is the test function, my script T, so defined, obeys the usual non-anomalous commutation rules. Okay, so we can conclude that even though I found this extension in the algebra, it's not homologically non-trivial. It's a trivial correction. There is no anomaly. Okay. However, okay. So before I proceed, let me also make an observation. This is perfectly fine because we know that there are no gravitational anomalies in 2+1 dimensions. So no surprise, exactly as we expect. However, we can impose a constraint on the theory, namely a constraint of incompressibility. And how do I do that? Well, I have a Hamiltonian structure, so I pick a constraint that imposes or carries the information that I have an incompressible fluid. Because it's Hamiltonian, I have to choose a conjugate constraint and eliminate them via Dirac brackets or Hamiltonian reduction. Okay, so if I do that, if I set rho minus rho bar times some constant equal to 0, then I can choose theta as the constraint conjugate to it because rho and theta are canonically conjugate to begin with. Okay, so I choose the conjugate constraint and eliminate the theory. And now I have a true anomaly in the theory. Why so? Because notice this term here involves a velocity. The term that I use to redefine and eliminate my anomaly here, but velocity involves di of theta. That theta is a gauge direction now under this new way of looking at it from the incompressible point of view. Okay, so it's a gauge dependent redefinition. So it's not acceptable. Therefore, now I have a true anomaly in the theory. Okay, and that's exactly similar to what we found for the case of the sigma. Okay, that's also what we get. Okay. Now, having understood that this is the genesis of how the anomaly can arise, we can now ask, can I reproduce the result that Paul had obtained earlier? Okay, so here's what I'm going to do. I'm going to keep this anomaly now because we are going to use the incompressibility condition, which is appropriate to the case which was discussed anyway. Okay, so then we're going to add to it to make two changes. One is this constitutive relation that I mentioned, the charge neutrality condition, if you like, okay, relating rho, rho bar, and omega, del omega. And then I'm going to add a homologically trivial term to T in like so. That's special to two dimensions because del cross psi in two dimensions is just proportional to a scalar. Okay, so I'm able to do that. And this extra term, and it is proportional to rho, so there is nothing, you know, undefined there. Everything is well defined, so it's a homologically trivial correction. Okay, so I add this term, and then I recalculate commutators for T tilde. Okay, and here's what I find. If I take the holomorphic combination and the anti-holomorphic combination and write down the commutator, here is what I get. And I'm just displaying to you this equation, but if you go back and check Paul's paper, this is exactly the equation that they have, okay? So we have reproduced exactly the commutator algebra for the energy moment tensor for this case by adding a topological term to the fluid action, okay? So what is the conclusion for this part of the discussion? Very simple. Here is the action. Term one and the Hamiltonian standard fluid dynamics. Term two in red is the topological term I add, okay? So one extra term. The last term is going to give you, upon variation of A naught, the constitutive relation that I mentioned, or the charge neutrality condition, which, not surprisingly, you know, you need something like that, and I coupled it to A naught, because that's a natural thing to do, okay? So this action, I claim, is the analog of Witten's Witten action for the Kac-Moody algebra. But in this context, this is the action that reproduces this commutation rules up here. Okay. So that's the first conclusion. Let me say a few more words about this. What about 3+1 dimensions? I can do exactly the same analysis. I can take the same topological term, but now I'm in one high dimension. And if you go back and look at this algebra, notice I have the vorticity here on the right side. That's no longer a scalar. Okay, that's now a vector in 3 dimensions. So I'm going to have a slightly different looking form for this. So let me write the vorticity in terms of a vector. The direction I call nk, the magnitude I denote as omega. So nk, if you like, is a unit vector giving the orientation of the vorticity at a given point. Yes, please.
Yes. Can you go back to the action?
This one?
So the red term is the additional term, right?
Yeah.
You said it's a Vesuvino-Witten term? Huh?
It is, no, what I'm saying is
So
that.
it's written in one extra dimension or?
No. I didn't mean to say that that is a Vesuvino-Witten term. What I'm saying is that in the analogy with the Kac-Moody algebra, right? You have a fermion-based derivation of the Kac-Moody algebra, and it gives you a commutator algebra for the currents, which is the Kac-Moody algebra, with a central extension. And then you have the Vesuvino-Witten action, which reproduces that directly. That's the analogy I want to show here. If you take the first line as the analog of the Kac-Moody algebra, the anomalous commutator algebra, you can ask what is the action that reproduces the analog of the Vesuvino-Witten action. And that is this term here.
But it's not really proper to call a Vesuvino-Witten action a topological action. It's not a topological term. Okay?
Oh, yeah, but it has an additional topological term, right? The central term comes from the existence of the topological term.
Yes.
And that's exactly the same here. The first term here is the standard kinetic term of fluid dynamics. This is,
But this is written in one extra dimension or not?
I'm sorry,
It is written in one extra dimension, like the Weizmann-Witten term, or not?
no, it is not.
So in principle, if it's a local term in the action, it's not an anomaly.
It is in the
Is it?
sense that trace sigma 3 G inverse DG is not well defined if you take the incompressibility condition. Okay, it involves a theta direction, which is a gauge direction, and therefore it is not well defined in terms of the fluid variables. That is the analogy. Okay, so similar to what I said about the sigma model. Okay, so it's another way to phrase this is, if you think of the anomaly, remember original Weizmann work, where they try to integrate the anomaly to get the Weizmann term. So they have, everything is defined, in that case, everything was defined on space-time, but there is a line of integration that you have to do. So there is an extra gauge direction.
Mhm.
What Witten showed was that that extra gauge direction could be interpreted as an extra dimension.
Yes,
Okay, but let's stick with the original Weizmann idea for a second.
yes.
Here I have G inverse DG trace sigma 3. It depends on two directions in G inverse DG are okay. They are just the two alpha and beta directions of Clebsch. They are referred to the incompressible fluid. The theta direction is extra. That's like the extra dimension.
Okay,
Okay, that's the analogy, if you
okay.
like. Okay, it's a very good point that you make, because one of the things I want to emphasize is precisely, well, I already said it in the context of the sigma model, but
Because if it is a local term in the action, it can be removed by renormalization. And
that's
so it
exactly
may
right.
be interesting, but not really. You
Yeah,
cannot
that's exactly
properly call an anomaly, right?
Absolutely. So here I remove it by a local term, as you see.
Uh-huh.
But once I have the incompressibility, the local term is no longer admissible because it involves
Right.
this gauge direction.
Okay.
Okay, that's exactly the point.
Okay.
Okay. Okay, so now let's go back to 3 dimensions. And all I have to do now is, okay, I'm going to take this direction n as a unit vector, giving the orientation of the vorticity. Omega is the direction, the magnitude. The constitutive relation of the charge neutrality condition is the same as before. And now I look at the algebra. Then I can reduce this algebra. Now I'm going to this algebra here. Reduces to this form. Okay. So there is a C here, C of K, a vector, which is effectively the direction of the vorticity. Okay. So what does it mean? It means the following, that if you look at vortex lines, strands of vortex lines, and you look at a transverse section, which is like doing 2+1 theory, you have the locations of the vortices and then the orientation. If you're in a small enough volume where the orientation doesn't change very much, it looks like what happened in 2 dimensions, except C is the vector giving you the orientation at that point. Okay. So you can still talk about this. In particular, if I'm in a small enough volume, that the orientation of the vortices is more or less constant. If I make that approximation, I can put it outside the integral. Now, remember, in the incompressible case, psi and psi prime are divergence free. They have to be like, it's incompressible, so that is the case. And such vectors can be parameterized on a 3 torus in terms of integers like this. Alpha and beta are some numbers, and then m and n are integers, and this is a general parameterization which is dense on a 3 torus. Okay, dense in the sense that these alpha and beta are linearly independent over the integers. So it's a criterion similar to what is used in the KAM theorem in mechanics. Okay, so you need to say that there is no particular combination of these guys with integers which vanishes. If I then it forms a dense set. If I do that, the extension takes the structure, and this agrees with some recent work that I quote here, which is talking about extension of on a torus. Okay, the reduction I did to an approximately constant nk was simply to show this connection. But the real theory of interest would be this, where n is arbitrary and you keep the c inside the integer. So it could be useful in 3+1 dimensions as well. Okay, finally, I want to go back to the term I call I2 for a second. If I can bring it up. So this term, which is proportional to G inverse dg cubed times C. Okay. Now, G inverse dg cubed, you recall, G inverse dg is what gave me the velocity. So G inverse dg cubed is proportional to V dV. It is what I called helicity earlier. Okay. It's exactly, it's the top rank, but it's like a Chern-Simons term. It's also the top rank differential form on the group. So I take that term and I look at the action. So now my topological term is this, and go through the same analysis. It's a little more involved, but it can be done. There's nothing terribly complicated about it. I get the standard commutator algebra plus an extra term. Okay, this B here is D of C, where C was a one form, as you recall, in 3+1 dimensions. And here is a structure. Okay, so there is an extension term that enters. And sigma here, which multiplies rho, is simply the density corresponding to the helicity. Okay, so the fluid helicity is this number, V dot omega, which is exactly this quantity, which you may recall if you have a compact group like SU2, that is the winding number of S3 map into SU2, and that's going to be an integer. Okay. And the density for that I call sigma, and that's what comes here. So this is a bit puzzling. You might ask, what kind of fluid are we talking about? So let me remind you, it's a Chern-Simons term that we added, VdV, it's a helicity, and because it's an abelian Chern-Simons term, when it is non-zero, it refers to knots. Okay, it does not give you the full-fledged knot invariance that you expect in the non-abelian theory, like Jones polynomials or the Humphrey polynomials or things of that sort. But it does give you some information about knots. And when you look at these knots, you can ask, can I, because this extension is related to that, I can ask the following question. If I consider a whole bunch of vortices, a dense collection of vortices, but they have knots in them, okay? And now I do a similar argument to what Paul did for the vortices themselves. Take the knots, tightly bound knots as point particles, and construct a fluid dynamics of the knots. How can they move around? Remember, these are knots. Diffeomorphism can move them up and down, and you can also change the directions, okay? Because, you know, you can do all the moves that you usually want to do with knots to do that. So therefore, I can actually move from one configuration of these knots to another, different locations on the vortices, as well as different distribution across space by doing diffeomorphisms. Therefore, in principle, I can construct a fluid dynamics for them, okay? And I expect, and this is somewhat conjectural, but I expect that this second topological term that I talked about is going to give you the Eulerian description of this knot fluid, okay? So let me just conclude then by saying the following thing. What we have done is simply to take the standard fluid action, add different types of topological terms, which are dictated to us by the nature of the fluid and in the group theory description. It's very natural what these terms are. If you do it in 2+1 with one of those terms, we can derive the anomalous fluid dynamics that applies to the vortex fluid. 3+1, again, interesting possibilities. Could be a knot fluid, could be, again, vortices, but orientation changes can be included, okay? So, and that brings me finally to the final transparency. Thank you very much for your attention. Which one? This is in 3+1. So I added a different topological term. So remember, so there are two types of topological terms I discuss here. The second one here, what I call I3, is what led to the fluid that you considered in your paper. Okay. The I2 is a new type of topological term which people have not considered in this particular context, at least not from the point of view I'm taking here. And if you add that, you can work out the anomalous commutator algebra. And that's given here. This algebra, this is the extension. And it is proportional to the density sigma of this helicity, fluid helicity that comes in. Okay. Now you ask, what is a physical interpretation? And I'm thinking that that could be in terms of a fluid of knots. Okay. There's a question there.
So just a quick question about the last conjecture. How would you differentiate different types of knots in this fluid? Like, why would you think there are knots and not like endpoints or something more mundane? I would think that, you know, if you said it was a fluid of knots, then maybe you would have a way of thinking that there might be specific interactions that undo these knots or do something like that, or so that you can then start classifying different knot fluids and so on.
Okay.
Is that related to why you're conjecturing this, or?
Yeah, I don't think there are transformations you can do to undo the knots because they are there, right? However, here I cannot distinguish between different knots very specifically for the following reason. This is an abelian Chern-Simons, and whatever polynomial you derive from it is a very coarse description. It does not distinguish between different knots. Even the Jones polynomial and the Home-Flip polynomial, we know, while you can derive polynomial for each of the knots, it is possible to have two different knots with the same polynomial, right? They don't always, it is not sufficiently discriminatory if I write the Jones polynomial between all possible knots, okay? It's not a 1-1 map, okay? Therefore, and this is even worse, it's abelian. So therefore, lots of different types of knots will have the same effect here. So I would not be able to distinguish that, okay?
Right, but there would still be some that you could distinguish.
Oh, there are some other things you can do to distinguish them. But with this particular topological term I added, I cannot distinguish that. There's a question there.
So in Chern-Simons theory, on a quantum level, even in a abelian case, there is framing anomaly. So you have to define, like on a non-zero manifold, you have to specify framing. Also for knots, you have to specify framing. Does it play a role here?
Not at the moment, no. Okay, because first of all, I'm not really deriving the knot invariance, right? I'm simply writing this helicity as an extra term, okay? And the framing does not affect this. However, having said that, if you were to fully quantize this theory, where you really have to take care of coincident points and singularity, resolve those singularities, then I think I would need framing for that. Okay. Remember, in the case of the Chern-Simons, that is closely related to the issue of writing. The framing is needed also to resolve the singularities that one encounters. Okay, so this is still classical. Okay, so I don't quite have that problem yet. Okay. Oh,
So what is the boundary condition for these vortex lines? They are open lines
Yeah.
or closed?
yeah, they're open lines, and I'm assuming they're fixed on the
Okay.
boundary somewhere. You could ask the question, what about some surface effects?
Yeah.
I have neglected all the surface effects here. This is the bulk description. It is a very interesting question to ask what the surface effects are, but that's second order, just didn't get to it, so to speak. Okay.
Because maybe these endpoints can be the two-dimensional vortices in one lower dimension, and you have some correspondence from 3+1 to 2+1.
I'm sorry, I didn't quite understand.
I'm saying that maybe these endpoints are your previous 2+1 vortices
Mhm.
on the surface, so they could have
Yes,
some
indeed,
non-trivial.
indeed. Yeah, so you're saying they end in a surface,
Yeah.
which is a 2+1 fluid.
Yeah. Exactly.
Yeah, it could be. I just haven't looked into that in that level of detail. Okay.
Thank you. Thank you.
I actually have a, sorry.
Oh,
Yeah, I have a couple of very basic questions.
sure, please.
So one is in the first part, you wrote the equations for hydro
Uh-huh,
as a sigma model with target SU1, 1. Is this related to some symmetry of the system? Is this I don't know, conformal
right.
symmetry?
It is, at the end of the day, I believe it is related to symmetry. You're not here yesterday when I talked about it. The idea is that, I mean, the way I view hydrodynamics is to say that point particles are unitary representations of your symmetry group. Okay. To start with Poincare, you can add on additional symmetries. So I need an action that reproduces that at the point particle level. That is the coadjoint orbit action. Now you make it into a fluid by taking a collection. Then you are getting naturally an action which is defined in terms of group elements. If I now take the Poincare group and reduce it to the case of a spinless fluid, because Poincare also has spin in it, then I expect I would get something like this. Okay. So it is related to a symmetry, but the symmetry is really the true symmetry that defines what a particle is. Okay, that's what I expect. Okay.
Okay. And the other question is, so these topological terms
Yeah,
probably come with a coefficient in front, which is probably quantized.
that's right.
So what will be the physical significance of these coefficients?
So for example, if it comes, if it's SU2, as Paul mentioned at some point, then it is related to the quantization of the vorticity and the helicity.
And then?
And the helicity, what I showed as helicity in the last one. Okay. If vortices carry unit charge in some units, then you have an integer multiple of that. That is a quantization that you would expect. Okay. So number of vortices, and then the overall helicity, which is the number of knots you can make. Okay. That's the thing. Yeah.
Thanks.
Yes. Yes. Possible. Sure. Yes. Yes, that's a possibility. Yes. Right. I looked at open vortices. Yes. Yeah, but if you do a diffeomorphism, they can kind of slant over this way. Yeah. No, I'm not saying it is attached to this. No, it could be closed ones. I did not talk about the closed ones because, this is the simplest thing to think about, actually. Physically, they're very different. And it could, I agree. So it could very well be what you're saying, namely little rings with knots in them and moving around. That is also possible. Okay. No, the word is conjecture because I'm still not exactly sure how to pin it all down. Yeah. Uh-huh. Mm-hmm. 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 Yes. Uh, I would love to hear about that because that's exactly this. Okay. Yeah. That's right. It was, yeah, exactly. That's right. And that is this picture here. Yeah, that's right. Indeed. Oh, I think I would love to hear that reference actually, if you have something. Okay. Okay. Thank you.
Can I ask a question?
Oh, Shinsei wants to ask a question.
What too late? Maybe just a quick question. Is that okay?
Go ahead, Shinsei, please.
So in the past, I think people computed the Poisson bracket of the coordinate of the vortex.
Uh-huh.
And then I think there's a claim that they found a Hop term like commutation relation for 3D vortex lines.
Right.
Is it related to, it's perhaps like more like a fast quantized version of what you...
That is exactly right. Yeah. That is the structure that was used in Paul's paper. You're talking about this structure here. Z bar with Z is delta alpha beta, right?
But there's a 3D work also.
Oh, in 3D. In 3D,
Yeah.
I don't know if any work doing that. If you know something, I would appreciate that. But that would still be the first quantized version. That is correct. Yes.
Okay. Yeah. Thank you. Perhaps yeah. There's a work by Matsuo, I think.
Oh, you're talking the Regge-Rossetti work. Oh, I see. Okay.
Yeah. There's the work back in 90s, I think.
Oh, right. Yeah. That would be the first quantized version. If you're talking Regge-Rossetti, yes.
Okay. Thanks.
There is a very beautiful paper by Regge and Rossetti, which I believe is around 1976, 77, where they constructed the, if you like, single vortex dynamics and talked about how to write actions and Hamiltonians and so on. It's a very, very, very nice. In 3+1. Yeah. Okay. So there is an extra term which looks very much like something of the form x dx type wedge product comes in. And that is crucial to get this non-commutativity of the transverse directions. Right here it says the transverse directions are Poisson conjugate. If you want to generalize that to 3+1, there is an integral you have to do. And that's a Regge-Rossetti term. Next. Yeah.
Yeah. Thank you. Yeah.
Okay.
Yeah.
Thank you. Thank you very much.